Hi, I'm Quinn, and today we're tackling something that sounds super intimidating but is actually pretty elegant once you get it. Quantum gates. Quantum gates are how we steer a qubit. Think of them as the moves in a choreography that turns a simple starting state into something useful. Picture this. You're driving through a city and you come to an intersection. Simple enough, right? You're heading north, the light turns green, you keep going north. Easy. But here's where it gets interesting. What if that intersection could change your direction based on specific rules? Like, imagine a magical intersection where, if you approach from the south, it flips you around to head east instead. If you approach from the west, it rotates you to face south. And so on. That's basically what a quantum gate does. It takes quantum information coming in one direction, one state, and transforms it into a different state based on precise mathematical rules. Unlike classical logic gates, quantum gates must be reversible. That's because they're unitary transformations. They preserve total probability. Instead of flipping a bit from 0 to 1, a gate rotates a qubit state on the Bloch sphere. So quantum gates have to be more sophisticated. They can't just flip a switch. They have to smoothly rotate, twist, and transform these probabilistic states. Let me give you some real examples. The Hadamard gate. Let's call this the confusion intersection. You roll up with a car that's definitely black, a qubit in state 0. You pass through the Hadamard gate, and suddenly your car is in a perfect 50-50 superposition. It's simultaneously black and white. You've gone from certainty to maximum uncertainty. This is like an intersection that takes you from heading due north and puts you on a diagonal. You're now going northeast, split between two directions at once. The Poly-X gate. This is the flipper intersection. This one's simpler. Black car goes in, white car comes out. White car goes in, black car comes out. It's the quantum version of a NOT gate, a simple flip. If you're driving north, this intersection spins you 180 degrees so you're heading south. Direct. Clean. Reversible. Now here's where it gets really cool. The C-NOT gate, the conditional intersection. This one requires two cars, two qubits. One's the control car, one's the target car. The rule is simple but powerful. If the control car is black, do nothing to the target car. But if the control car is white, flip the target car. Imagine two lanes approaching an intersection. The car in lane 1 is the boss. If it's black, the car in lane 2 just cruises through unchanged. But if the car in lane 1 is white, the intersection flips the car in lane 2 to the opposite color. This is how qubits get entangled, where the state of one becomes fundamentally linked to the state of another. It's the foundation of quantum magic. Quantum computing gets truly interesting when we use two-qubit gates. The most famous is C-NOT, which flips one qubit if the other is 1. If the control qubit is in a superposition, C-NOT can create entanglement. That's the key ingredient for many quantum algorithms. Each quantum algorithm is basically a choreographed route through the city. Your qubits are the cars, the gates are the intersections, and the route you design determines what computation you perform. The beautiful part? These gates are reversible. Unlike classical logic gates where information can be lost, quantum gates preserve information. It's like every intersection remembers where you came from, so you can always trace your path backward. In practice, gate quality matters. Real hardware has noise, so deeper circuits accumulate more error. That's why quantum engineers obsess over gate fidelity, calibration, and minimizing circuit depth. The takeaway: quantum gates are the basic controls of a quantum computer. Single-qubit gates shape superposition and phase. Two-qubit gates create entanglement. And a small universal set lets us build everything from those primitives. That's all for today. Take care.